A mass of 1.8 kilogram of air at 120 kilopascal and 34 degrees Celsius is contained in a piston cylinder device. The air is now compressed to a final pressure of 600 kilopascal. During the process, heat is transferred from the air such that the temperature remained constant. Calculate the boundary work during this process. So we know the boundary work is equal to from state 1 to state 2 PdV. So to take the integral, we need to know how to represent P in terms of V. And one way is to use ideal gas equation. And we can assume air to be an ideal gas. Why? The critical pressure and critical temperature given can be compared to the temperature and the pressure of that system. So the temperature is 34 degrees Celsius plus 273 gives you 307 Kelvin. The pressure is 120 kilopascal, which is 0.12 megapascal. So if you take a look at that, the critical point data, 0.12 megapascal, which is the pressure of your system, is much lower than 3.77 megapascal, which is the critical pressure. So for at low pressures, remember, we can assume the gas to be an ideal gas. And besides that, the temperature we have is much higher than the critical temperature. Again, this also validates the approximation we are doing and assuming air as an ideal gas. Okay, so basically, then let's use ideal gas equation. PV is equal to MRT. Solve it for P, MRT over V. And we can plug this in here. And now if we take the integral, wait a second. If we take the integral, since mass is a constant, because it's a closed system, R is also a constant, it is gonna be the MR term is gonna get out because they're constants. And besides those, the temperature is also constant in this process. So MRT is getting out of the integral, only 1 over V remains within the integral. And if we take the integral of that term, this should give you ln V2 over V1. Okay, so they're asking us to calculate boundary work, and we ended up with an equation based on the assumptions that air is an ideal gas. And here the mass is given to you, R is known, and the temperature is also known. And what about volumes? Okay, do we know V1 and V2? Well, we don't. So, but there is this thing, if you remember, we know this relationship P1 V1 is equal to MRT1, P2 V2 is equal to MRT2. If you solve both of them for MR, because this is a constant, the term will stay the same for first and the second state. Since left-hand side of both equation is the same, that means P1 V1 over T1 is equal to P2 V2 over T2. In this problem, T1 is equal to T2, so we cancel those out. That means P1 V1, right, is equal to P2 V2. In other words, P1 over P2 is equal to V2 over V1. Okay, so what we can do then, instead of this term right there, I can replace this with P1 over P2. So the boundary work is equal to MRT ln P1 over P2. And here mass is 1.8 kilogram, R is 0.287 kilojoule per kilogram Kelvin, and the temperature is, in terms of kelvins, 307 Kelvin. And continue to this equation is times ln P1 is 120 kilopascal over 600 kilopascal. So this should give you boundary work to be minus 255 kilojoule.